everybody. Today I'm going to be going over kinetics. Kinetics is the study of the rate, also called the speed of a reaction, and the factors that affect the rate. Chemical reactions occur as a result of collisions between molecules. Some reactions happen quickly while others can take years, which is why kinetics is an important part of chemistry. This video, along with the note outline and poster that are a part of my project, covers reaction rates and rate laws, reaction orders, and the relationship between reaction concentrations and time. Check out Noah's project for more kinetics-related materials. Here we have two different energy diagrams. The reaction represented in A is endothermic because the products have a higher potential energy than the reactants, and the delta H is positive. The reaction represented in B is exothermic because the products have a lower potential energy than the reactants, and delta H is negative. As mentioned, chemical reactions occur as a result of collisions between molecules. If they collide at just the right orientation, they can get over the activation energy, which is represented by the purple arrow. An activated complex is a structure that results in the maximum energy point along the reaction path. This is represented by the pink dot. The reaction rate is the speed of the reaction, or the speed at which the reactants are turned into products. The rate of a chemical reaction is proportional to the number of collisions between reactant molecules. The more often reactant molecules collide, the more often they react with one another, and the faster the reaction rate. There are several factors that affect the reaction rate. Increasing the concentration of a reactant increases the number of collisions between reacting species per second, and therefore increases the reaction rate. The concentration of a gas is a function of the pressure of the gas. Increasing the pressure of a gas is the same as increasing its concentration. Under higher pressure or at a higher concentration, gas molecules collide more frequently and react at a faster rate. Temperature is proportional to the kinetic energy of the particles in a substance. At higher temperatures, particles collide more often and with more intensity. A catalyst is a species that speeds up a chemical reaction without being chemically changed by the reaction. As mentioned, only collisions involving particles with sufficient kinetic energy result in the formation of an activated complex. A catalyst provides an alternate pathway for the reaction, a pathway that has lower activation energy. This means that there will be more successful collisions. The rate of reaction of a solid substance is related to its surface area. In a reaction between a solid and an aqueous, liquid, or gas species, increasing the surface area of the solid reactant increases the number of collisions and therefore increases the rate. The reaction rate is generally defined as the change in concentration over time and is measured in molar or moles per liter per second. Take this example. It's a simple reaction. We have some A and it will turn into B. Because we are starting out with A, the change in concentration of A will be negative. The reaction is progressing in the forward direction, so the rate is positive. This is why there is a negative sign in front of the reaction rate of A, so that it will equal the reaction rate of the reaction. If you're given the rate of one species in a reaction, you can compare the reaction rates using mole ratios. Let's use this reaction as an example. This is the equation for the synthesis of ammonia. If we are given the rate of depletion of nitrogen gas, then we can find the rest of the rates. The rate of depletion of nitrogen gas is negative because it's being used up in the reaction. For every 1 mole of nitrogen gas used, there are 3 moles of hydrogen gas used. Therefore, we multiply the rate of depletion of nitrogen gas by 3 and get the rate of depletion of hydrogen gas. This is also negative because, like nitrogen, it is on the reactant side. For every 1 mole of nitrogen gas used, there are 2 moles of ammonia produced. Therefore, we multiply the rate of depletion of nitrogen gas by 2 and get the rate of formation of ammonia. This is positive because ammonia is being produced by the reaction. The overall reaction rate is equal to the rate of the species only if that species has 1 mole in the balanced equation. In this case, it is equal to the negative rate of depletion of nitrogen gas. This means it is equal to the negative rate of depletion of hydrogen gas divided by 3 and the positive rate of formation of ammonia divided by 2. This is simplified in the equation on the bottom of the slide. A rate law is an expression that shows how the rate depends on the concentrations of reactants. This is the equation for rate law. It is the rate constant K times each reactant raised to its reaction order. The concentrations of the reactants have to be raised to some power to show how they affect the rate of the reaction. These powers are called the reaction orders and are represented by M and N. The higher the reaction order, the more the reactant affects the rate of the reaction. Usually, reactant orders are 0, 1, or 2, 2, but they can also be fractions or even negative. The sum of these reaction orders is the overall reaction order for the reaction. As a side note, the rate constant K is not affected by concentration, but it is affected by temperature and catalysts. Increasing the temperature will increase the K value and therefore increase the reaction rate. The addition of a catalyst will increase the rate of a reaction, meaning the K value would increase if the concentrations remain constant. If the reactant has a reaction order of 0, then changing its concentration does not affect the rate law at all. This is because anything raised to the power of 0 equals 1. If the reactant has an order of 1, then whatever happens to the concentration happens to the rate. If you triple the concentration, then you also triple the rate. If a reactant has a reaction order of 2, then whatever happens to the concentration happens to the rate squared. If you triple the concentration, then you must multiply the rate by 9. If a reactant has a reaction order of 3, then whatever happens to the concentration happens to the rate cubed. If you triple the concentration, then you must multiply the rate by 27. As mentioned, the sum of the reaction orders is the overall reaction order. Most reactions are below third order. However, third order reactions are definitely possible, just much less common. Reactions of even a higher order are possible, however, they are extremely rare. The rate law of a first-order reaction is the rate constant times the concentration of the first-order reactant, or the pressure of the first-order reactant if you have a gaseous system. For future reference, you can replace concentration with pressure in any of the equations I'll go through for the remainder of the video if you have a gaseous system. The unit of the rate constant in a first-order reaction is seconds to the negative 1. To find the reaction concentrations over time, you can use either of the next equations. The subscript T means at a specific time, and the subscript 0 means initial. Plotting the natural log of the concentration of A versus time results in a straight line with a slope of negative K. The half-life of a reaction, which is represented by T subscript to the 1/2, is the time required for a reactant's concentration to drop half of its original value. In first-order reactions, the K value times the half-life always equals the natural log of 2. This means that the half-life is independent of the initial concentration and is constant throughout the reaction. Everything on this slide and the next slide only applies to reactions that are second order in one reactant, not first order in 2 reactants to have an overall reaction order of 2. The rate law of a second order reaction is the rate constant times the concentration of the reactant squared. The unit of the rate constant in a second order reaction is molar to the negative 1 and seconds to the negative 1. This next equation is how you can find reaction concentrations over time. This is different from the first order reaction because there are no natural logs. Plotting the inverse of the concentration versus time gives a straight line with a slope of positive K. In second order reactions, the half-life depends on the initial concentration. The half-life times the K value equals the inverse of the concentration. The half-life increases as the concentration decreases, which is represented by the graph. The next part of this video kind of goes back to the factors that affect the reaction rate that I talked about in the beginning. If you refer back to the slide about rate laws, you'll notice the note at the bottom that says that the K value is affected by the temperature and catalysts, but not concentration. The equation on this slide relates the rate constant at 2 different temperatures with those temperatures. The activation energy should be in joules per mole, the temperature should be in Kelvin, and R is a constant that is equal to 8.34 joules per mole Kelvin. This is the first free response question I'm going to go over in this video. Please pause to read it. For part C, you're going to have to review reaction mechanisms, which I did not cover in this video. Part A asks us to explain how the graphs indicate that the reaction is second order. We can identify that this reaction is a second order reaction because the graph of the inverse concentration of nitrogen dioxide is linear with a positive slope. For part B, we have to write the rate law. Because this is a second order reaction and there is one reactant, the rate law is expressed as rate equals K times the concentration of nitrogen dioxide squared. For the first part of part C, it asks us if the rate law described by mechanism 1 is consistent with the rate law we wrote in part B. For reactions that have multiple steps, the slowest step is the rate determining step. This means that we will use the first step for the rate law. For an elementary step in which the reaction is a reactant plus that same reactant equals a product, the rate law is rate equals K times the concentration of the reactant squared. This means that the rate laws do match. For the second part of part C, it asks us if the rate law described by mechanism 2 is consistent with the rate law we wrote in part B. We will use the second step of the mechanism for the rate law because it is the slowest. The rate law for this mechanism equals K times the concentration of dinitrogen tetroxide. However, we cannot use N2O4 in the rate law because it is an intermediate. In step 1, the equilibrium constant can be used to substitute the concentration of N2O4. This would mean that the concentration of N2O4 equals the equilibrium constant times the concentration of nitrogen dioxide squared. Using that substitution, the rate law is consistent with the rate law from Part B. This is the other free response I'm going to go over in this video. Again, please pause to read it. This question has more math in it, so you will definitely need a calculator. Part A asks how many moles of X were initially in the flask. We can find this by using the original molarity and the volume of the flask. If we multiply 0.00633 moles per liter by 5.00 liters, we get 0.0317 moles of X initially in the flask. In Part B, we have to find how many molecules of Y were produced in the first 20 minutes of the reaction. Step is to find out how many moles of X are left in the flask after 20 minutes, and then compare that to the initial number of moles of X in the flask. To find the amount of moles left after 20 minutes, multiply 0.00427 moles per liter by 5 liters, then subtract that amount from the initial number of moles of X. Now use stoichiometry to find out the number of moles of Y produced after 20 minutes. Part C asks the order of the reaction with respect to X, which can be identified using the graphs. The second graph is the natural log of the concentration of X versus time and is linear with a negative slope. This is consistent with a first-order reaction with respect to X. Part D asked for the rate law. Because this is a first-order reaction, the rate law equals K times the concentration of X raised to the first power. Part E asks for the value of the rate constant in its units. Because it is a first-order reaction, we already know that the unit for K is time to the -1, whatever the time unit is, and in this case it's minutes to the -1. We can calculate K using the equation KT equals the natural log of the initial concentration divided by the concentration at a specific time. For this question, you can compare any 2 points, but I just chose the first two, and the work is on the slide. Part F wants us to calculate the concentration of X in the flask after 150 minutes. Another version of the equation used in Part E is KT equals the natural log of the initial concentration minus the natural log of the concentration of that time, and that was derived using log properties. And at the end, you have to use an E to get rid of the natural log and find the concentration, and that is not shown on the slide, but it is the last step. These are my sources for this video. There's a document with all of these sources and the slides that they go with if you are interested. Have a great day!